Hey everybody, I'm Anton Borisov from Fresha, where we do a lot of interesting data engineering stuff. And one of the stuff that we've done recently is StarRocks, and we use this query engine for Iceberg as well. So basically, this is the title of the talk, Breaking the Ice with StarRocks. And basically, you know the Iceberg. So Iceberg is actually kind of like a file format, and it's huge. So imagine like a huge, gigantic iceberg, and this iceberg is actually need to be broken efficiently in order to be queried. So right now we are about to discuss different ways to break iceberg, not only kind of like by partitions and kind of like metadata and by specification, but also with some help of query engine. And I think like StarRocks is very interesting query engine, and it has a lot of things to offer for working with iceberg. So shall we begin? So please raise the hand who tried or used StarRocks. Okay, that's much more than I expected. Okay. And who actually heard about StarRocks? Okay, much better. So I will stop a little bit to discuss what is basically StarRocks. So StarRocks is MPP engine, highly vectorized for executing real-time and lake analytics with, I don't know, sub-second latency most probably. And yes, so how is it possible? So, I mean, like you have an iceberg or any other kind of like lake format, and you want to execute it as fast as possible. So the answer is, as always, you need to highly parallelize it and efficiently cache it. So how to do it? There are two modes of deployment, shared data and shared nothing mode. For shared data, okay, you need to manage your metadata efficiently. So you need front-end nodes. That's exactly here. So it's catalog management, fetching the metadata, doing the query planning, and so on. And then you have like all the hard workers that are actually compute nodes, where the execution engine written in C++ with CMD and vectorized execution, so all the power lies here, is actually doing all the hard work. And then you have a separated storage. In this case, it's living in object storage, so S3 or HDFS, and that's it. That's shared data. What if you need like real-time latency, kind of like, and you don't wish to actually trade off like this elasticity? Because basically CN nodes in this kind of like setup, they're stateless. So it means you still use some local storage, but just like as an ephemeral cache, and that's all. But what if you want to trade elasticity for more real-timeness? Also possible with StarRocks, and you basically just do the same, but this time, your data is actually stored in local storage. This is kind of like range of data that are not intersecting between each other. And that's it. Now you get like more real-time latency. So two ways of deployment, flexible. I like this. So another part of StarRocks is actually federation. And federation are possible with external catalogs. And external catalogs is basically, you have an internal catalog, so in StarRocks native format that is highly optimized to do an all-app execution. And then you can connect Postgres database, MySQL database through JDBC catalog, for example, Elasticsearch through Elasticsearch catalog, and then you can connect Iceberg, Pymon, Hoodie, Delta, all of these different file formats through catalog. But the best of all of this is basically that you can actually execute federated query. So you can have a data from Elasticsearch, query StarRocks internal format, and join with some data from Iceberg. And it's all in single query. That's neat. Okay, basically right now I need to discuss a little bit like architecture. So basically in Fresha, we delivered the first StarRocks deployment in Britain in production, and we basically use this architecture. So it's by no means complete. It's simple, just to show how the things are actually connect to each other. So the first thing that I should talk is source plane. We use Postgres database and we CDC the data with Debezium to Kafka. Then we need to use some compute plane to transform and do something with the data. Then we have sync plane to get this data back to Postgres, to Kafka, to Iceberg, or to StarRocks. And then we have like a lake plane. And with a lake plane, you basically query the data. In our case, it's StarRocks with external catalog with Pymon, because we still use Pymon for some real-time data in compute plane. That's why the arrow with the compute plane as well. And then through external catalog, like keeper, we query Iceberg. So it's a little bit the same view, but it's more kind of like conceptual one. So we have basically 4 ways to separate the data. And this is kind of like ingestion plane. So we basically care about like what data we have and how to deliver it in Kafka in order to consume. Then this kind of like plane is mostly used by real-time lane. So if you need to do some transformation, we do it with Flink, and then we load into StarRocks internal with ingestion, and then we query in our dashboards or just some kind of like analytical queries or whatever. Then we have a historical lane, and it's basically for historical data. So for example, if you don't need the data, if you need some cold data, it doesn't make sense to store everything in StarRocks internal because it would be more costly and less, I don't know, like storage efficient, let's say it like so. So basically you can offload your data in Iceberg, and most of the times your query only hit like real time because you care about real time. And then when some of these queries needs to process some data 10 years ago, just go to the Iceberg and it just works in the same query. Just you maybe need to do some union all, hide it with dbt, but yeah, the idea is simple. And then some specific like Elasticsearch, StarRocks ES catalog, just to demonstrate, and yeah, we use it. And yes, let's go actually to Iceberg part because that's the most interesting. So I'll be quick because we don't have much time, but also this topic is very dense. So let's start quickly. Metadata cache. So imagine that you have your metadata, and in order to start a query, you need to plan your query. But in order to plan your query, you need to download metadata. And downloading metadata, it sometimes takes more time than to actually the query. So that's actually the question that StarRocks solved, I think, elegantly, because you can compare the pictures. So with no cache, you just go straight to catalog and fetch manifest files, and you just end up parsing and manifest. Visual Iceberg. What can we do better? Of course we can. We basically can cache the metadata, and the more data is historical, the more you don't care to actually kind of like how often this metadata is refreshed. But you may actually get like some sensible interval of refreshing this cache, and once in 1 minute or 5 minutes, this metadata is refreshed asynchronously. But most of the time, you don't spend time on planning the queries. You just fetch it from metadata cache, and that's it. That's smart. So that's one way of breaking the ice with Iceberg to a nice little cubicles. Then data cache. So before it was metadata cache, now it's data cache. The next time it will be cache. Who knows? Okay, so it's almost the same. But yeah, imagine that you kind of like spend time to plan your query. Then you need to actually fetch these Parquet files from object storage. But it's slow. What if you have some kind of like data ranges that are actually used by all the queries? Would it make sense to actually decode and save them in some cache? Yes, it makes sense. That's exactly what StarRocks is doing. So, and also watch these kind of like errors, because CN nodes can interact between each other to fetch the data that is not present in their local cache, but they can go through RPC and fetch from another data cache. And more on that, if your kind of like local storage is actually overloaded, like your disk is actually overloaded, it can be decided like dynamically that it actually time to go and fetch this object, this Parquet file through network to object storage. Because sometimes it makes sense, because if your IO is overloaded, maybe let's go to network. Okay, then planning. So you can have local planning and distributed planning. And this is kind of like a little bit of the edge between front-end nodes and CN nodes in this case is a little bit vague and disappearing, because with local planning, I hit my front-end node with some query, and front-end node, I kind of like knows, okay, this query is small, I'll handle it by myself. And it just kind of like uses the cache, goes to catalog, fetches the manifest, prepares the plan to be executed by CN nodes. But what if the query is actually needs to fetch 200 manifest files? Each of them is 8 megabytes. I mean, like you have less front-end nodes than CN nodes, because CN nodes are actually the horses, heavy horses that actually execute this stuff. They have more RAM, more CPU, and it means that you basically can offload this stuff to CN nodes, and these CN nodes would actually, in parallel, execute this fetching of the data, metadata, sorry, and then return to the front end, and it would be much faster than to actually plan by a single front end node. Okay, materialized views. So that's another cool feature from Iceberg. And basically, look at the picture. So on the left, you have kind of like two inner joins. And imagine that we declared like, so, and this inner join, maybe it has some aggregation or other kind of like stuff where you actually need to scan a lot of data. But then in the end, it's only a couple of rows, so maybe a single value that you actually care about. Imagine that you declare materialized view, and then when in your query you actually write inner join, it would actually be rewritten to use materialized view, and this materialized view wouldn't actually go and plan and execute this query, provided that the data is still the same. You can actually refresh this materialized view, and the StarRocks team is actually working about making it more incremental, but even now you can actually use your partitions and have like partition-wise materialized view refreshing. So in case of Iceberg, it's very smart and neat, and it's another way how you can actually reduce your planning and execution overhead. Okay, now to the most beefiest part. So how Iceberg Read is actually working in StarRocks. So as you know, there is positional deletes and equality deletes in Iceberg specification. So positional deletes are easy, but unfortunately, most of the streaming engines, they actually write equality deletes. So you can treat equality deletes as some kind of like predicates, like where field equals something. And that's all that you know. I mean, like if we used only positional deletes, it would be super easy. And actually positional deletes are handled in StarRocks very easily. You just have Iceberg delete builder. It constructs bitmaps and then uses this bitmap to filter data files, the actual packet files, from rows that are not needed, that were actually marked as deleted. For equality deletes, it's a lot more complicated. You actually need to do the anti-join with a hash joiner actual class from StarRocks that actually handles this kind of like, okay, I need to understand what rows we actually deleted and how to exclude this row. So it's an actual join, and this join can be very high cardinality. That's a problem. Okay, as I said, like the main idea of StarRocks as a query engine is to execute as many ranges, scans, and as much work in parallel as you can. How to do it? Because imagine that you have like a pipeline where you are choking on some heavy equality delete anti-join. Your whole pipeline is actually waiting for the data to be returned. So there is a neat solution from StarRocks for this. So basically, it's using queues. So you have like remote files, get remote files asynchronous, it's incremental, so it's kind of like you can start working as soon as you receive the data. Then you have remote source trigger, and then the work is actually kind of like separated to a different queues. So there is a queue with equality delete, without equality deletes, and with only equality delete files. And all of these things can be processed by any CN node and any thread. And that way, it's actually working in the most parallel fashion that you can even achieve with a query engine. So this is like a more pipeline with a more sequential view. So scan range data files. You read positional deletes files. Then you use Iceberg delete builder to construct these bitmaps. And then this data is actually prepared so you kind of like get cleaned data files that need to be cleaned from equality deletes. How to do it? So this is equality delete lane, and all these kind of like passes. So you read equality deletes, you construct like a join, then you has joined like clear data and the data that needs to be deduced, what is deleted to and what's not. And then in the end you have result chunks and matrix probes. And this kind of like the faster you get some data, the faster other kind of like nodes start processing the data. So this is a pipeline. So once again, full picture. So front-end node is actually responsible for Iceberg equality rewrite rules. So planning, as I said, like they can get some help from CN nodes in order to plan efficiently. Then there is a plan thrift part that is like an intermediary, because when you plant, you need to send this work for the actual backend CN nodes execution. And that's exactly what we talked about. So you have Iceberg delete builder with delete keys chunks, clean chunks, and other stuff. So you have hash joiner and then result. All good. So the big news. StarRocks 4 was recently released, and they actually implemented a lot of neat stuff for specifically Iceberg, because Iceberg is the main data lake format supported by StarRocks. So they actually added local sort to to produce Parquet files physically for faster reads. So if you write Iceberg files with StarRocks, it's very efficient because it's basically like that order. Support. Then they have full support finally for creating and writing hidden partitions in Iceberg tables. Then they had count min max queries that don't actually touch data files. They only consult metadata and stats files to actually quickly understand what files they need to, what would be the number to display and what is actually missing to download. It's very fast. It's very exciting because analytical queries benefit from this feature very much. And they improved optimizer, because I believe I haven't mentioned, but StarRocks is running CBO cost-based optimizer, and they spent 2 or 3 years since they forked their project from Apache Doris to optimize it super heavily. So that is very. So they continue evolving in this, and basically you see the picture. So all of these improvements is actually resulted around like 40–50% improvement on query execution time since StarRocks 3.3 version. And they use another query engine, but I guess it's an euphemism for Trina, because they usually compare with Trina. Okay, so another 4 things to remember. StarRocks 4, I don't know, like somehow number 4 is creeping into my presentation. So bullet points. Frontend handle all metadata complexity and routing logic. So frontend is used only for this. You know, it's not completely true because you can get help from CN nodes, but nevertheless. Backend just executes simple operations, scan with bitmaps, scan for anti-joint. It's dumb, but it just knows how to execute something with highly parallelizable, vectorized execution, whatever, like all the best parts that you can get from C++. Queues provide a natural parallelism and work distribution for CN nodes to execute your kind of like scan ranges in the most efficient way. And incremental processing is actually kind of like keeps memory bounded regardless of table size. So it's actually adaptive. So if you have like spare CN nodes memory, then you can actually have a bigger batch, and it's actually kind of like happening dynamically in real time. So that's me. This is my LinkedIn, so if you want to connect and speak about Iceberg, StarRocks, and other real-time stuff with me, I would be happy. And I sometimes write in data engineering blog for Fresher, and I discuss Flink, Flows, Kafka, Postgres, Iceberg, Pymon, a lot of data engineering stuff that I feel you're interested in since you're there. Thank you. Any questions?
We do have a few minutes for any questions if anyone has. Yeah, one from Victor.
Okay, returning a question.
It's a nice one. If tomorrow would be like a Christmas and you will meet the Iceberg Santa Claus, what would be like thing you would be like a wish? What, like, just to translate, what is like the thing you miss in Iceberg, and especially maybe towards the StarRocks? I mean, maybe UDF, I don't know.
Okay, that's a broad question, and I don't wish to stop here like for 5 minutes talking, because I'm actually preparing an article about like Iceberg CDC, because right now I don't believe in Iceberg CDC, but I have that there are a lot of things happening with Iceberg v4 specifications that would actually reduce this pain and make this kind of like Iceberg CDC more feasible than it is, because the things like root manifest, like this global lineage, because when you last arrived in London and you had a presentation from Vakama, you actually mentioned lineage. And I think like lineage is the most important part that actually kind of like holding Iceberg to be really CDC friendly. Because I want to go to Lakekeeper and say like, okay, I want to get all the files since this last snapshot, and I have a guarantee that nothing happened since this last time. And this should be a consistent mark for all transactions, all tables, because right now it's actually, you can get a consistent view for a single table, but if you wish to have a consistent view for multiple tables, this is kind of like a little bit complicated, and you actually kind of like need to align and do some additional transformations or bookkeeping.
Cool. You know, sometimes you write the letter to Santa Claus, so maybe open the GitHub issue.
Okay, I'll write an article for Santa Claus, you know?
Cool. Okay. Any other questions?
Hi, I'm Dennis from AWS S3 Tables. So it's not quite the general Santa Claus question,
Okay.
but if you had like a wish to compaction algorithms or statistics to make your engine even faster, like by being able to ignore more data that you're currently not able to ignore, having better statistics, having different sort orders, from your experience, what would you like there?
Well, I mean, like generic statistics is fine, like unique numbers. So the basic, like the stuff that you have, like in Postgres, for example, when you have like the statistical information from PG statistics, it's kind of like Iceberg has it, but not that sophisticated like in Postgres, no functional dependencies and other stuff. So I think like Iceberg has a lot of things to borrow from the general databases, because they actually depend on the same stuff, how to prune effectively and how to reason about like how to execute query efficiently. And it all boils down to statistics. So right now, for example, StarRocks internal format just kind of like performs better because it has their own metadata and statistic, and it's pretty sophisticated. Iceberg is doing well, but still kind of like the performance is not as quite good as StarRocks internal, just for the same reasons.
Okay, thanks.
Perfect. Any other questions? Not the case. Well, Anton, thank you very much for your presentation.
Yeah, it was my pleasure.
And guys.